Okay, in this last lesson on one-way Anova, we are going to test the equality of three or more population means. The assumption is going to be that the means are equal to each other, but what we're going to do is we're going to analyze the sample variances of each of these different groups. We're going to use data from a population broken down into the different factors. So a good example of this would be, let's say I wanted to compare the GPAs for DMAC students, and I decided to categorize all of DMAC students into whether or not you are a first term student, second term, third term, fourth term, fifth or sixth term. So if I was going to use the strategies that we had in our section on comparing means, we'd be going back and doing t-tests and looking at things in pairs. So I'd compared like the first term students to the second term, first term to the third term, first term to the fourth term, and then after I've compared all that up, I'd go back and be comparing the second term to the third term students and so forth. And so what you're realizing here is that, my gosh, we'd be doing a bunch of paired testing and we could be here forever. So the Anova is going to provide us a very, very fast way of evaluating that scenario. It involves using the F distribution because actually we're going to shift gears and not so much look at the means, but we're going to be looking at the standard deviations and basically trying to see if there's any overlap between the standard deviations or if they're all very different from each other. So in a nutshell, we're going to be using the F distribution. Now if you remember, the F distribution involves a different table for each alpha. So it again becomes very, very complicated. Just to remind you, the F distribution is not symmetrical. It's right-tailed, very much like the arc chi-square distribution. The shape of it actually depends on the two different degrees of freedom. But remember, you were taking your standard deviation, the larger standard deviation, divided by the smaller standard deviation when you were doing that paired comparisons. So again, you'd be doing that comparison multiple times, but the Anova is going to do this all for us in StatCrunch. The requirements are that the distributions are approximately normal. This is not going to work for skewed distributions. The populations have basically similar, the same variances or standard deviations. Simple random samples of quantitative information. The samples are independent of each other. And they're only categorized in one way. So our example of looking at GPA, grade point averages for DMAC students and then grouping them by the number of terms would all be a good example of this. So our HO and our HA again are going to be a little bit different. This HO, our null hypothesis, is that the mean of the first population is going to be equal to the mean of the second population, of the third population, and onward. That's very similar to the null hypothesis that we had for, I believe it was goodness of fit. But there we were looking at the proportions. Our alternative is at least one of the means is different from each other. If you want to find out which one is, you could go back and analyze. We're going to have a table here that we can easily take a look at that. But perhaps there's more than one mean that is different. And so if there's several, you would definitely want to use a stronger statistical package than what StatCrunch is going to do for us. StatCrunch is only going to tell us if at least one is different from the others. So our F statistic is we're actually looking at the variance between the samples divided by the variance within the samples. And this is a discussion in regard to that. I am not going to ask you to implement anything with that, but that kind of gives you an idea as to what StatCrunch is going to be doing. So in StatCrunch, we're going to go to Anova, Stats, Anova, one way, select our columns, and then compute. So we've got two problems that we're going to take a look at here. A medical researcher wants to determine whether there is a difference in the mean length of time it takes three types of pain relievers to provide relief from headache pain. Several headache sufferers are randomly selected and given one of three medications. Each headache sufferer records a time in minutes it takes the medication to begin working. So at that 1% alpha, can you conclude that the mean times are different? Assume that each population of relief times is normally distributed and that the population variances are equal. Again, that assumption is important for Anova to be effective. So we've got these very small data outcome here, but we have 4 people who took medication 1, 5 for medication 2, and 4 for medication 3. And we want to see if the response times are different for any of one of those. So our null hypothesis is that the average time it takes for the pain reliever to be effective is all equal. The average length of time is equal for these three populations. The alternative is that at least one mean is different from the others. So again, we're going to go to StatCrunch. I have all of that information in here. We're going to be using columns 1, 2, and 3. That's where I have the medication information. So I'm going to go to Stats, Anova, One Way, and again I'm going to have to hit the Control key, but I'm going to select the first 3 columns and then down to Compute. And this is going to give us all of our information. Now notice the column statistics, it gives the average, standard deviation, standard error for each of these, but we're looking at the means. We're trying to compare and see if these are equal to each other. So the average for the first medication is 14 minutes, the second one is 17 minutes, and the third one is 16 and a half. Those are pretty close. 14 is a little bit less than the other, but is that statistically significant? So we're going to go down here to our Anova table. We can see that our F-stat is 1.5, and the p-value for that is 0.269. And really, we're only going to be looking at this one method, looking at the p-value. The p-value is high, so the null must fly. So in other words, that is not statistically significant. So from StatCrunch, we recorded our test statistic, our p-value. We have to interpret that though. We failed to reject the null hypothesis. This is a high p-value. This is within the normal range. There is not enough evidence to conclude that the means are different. Okay, for our next example, we have a table that shows the cost per mile in cents for a random sample of vehicles. So at a 1% alpha, can we conclude at least one mean cost per mile is different from the others? So I've got 5 small sedans, 6 medium sedans, 6 large sedans, and 4 SUVs, and 5 minivans. And we've got the average cost per mile for each. So we are going to find out if the average cost of operating the vehicle is different for these 5 different populations. So our null hypothesis is that the mu's are all equal to each other. The alternative is that at least one mean is different. So again, I'm going to go to StatCrunch. I need to close down our last problem. And I put this information in var 5 through 9. So I need to go into Stats, down to Anova, One Way, and I'm going to scroll down here so I can see my 5 columns. I need to hit the Control to select var 1, 6, 7, 8, and 9. And I go down and click Compute. And again, I've got my column statistics here, and I'm really interested in those averages, the means. So I've got 46.6, 59, 74.5, 76.5, and 64.5. So 76.5 is our high, 46.6 is our low. That's quite a spread. But it looks like this kind of clusters toward the high end. 46.4 is quite low. Is it statistically low and different from the others? And so we go down to our Anova table. Our F-stat is 13.097. I guess I could compare that to a critical value from our F tables, but we're not worried about our F tables. They're pretty long and arduous. But I'm going to go into, well, actually, I can't get to that, sorry. Our p-value is super, super low. That is much, much less than our alpha of 0.01. So that's a low p-value. Our null must go. So that's the method that we're going to use on Anova, is the p-value, evaluating that. So because that is so low, we are going to reject the null hypothesis. There is sufficient evidence to conclude that at least one mean cost per mile differs.